So my name's Max, and I'm going to talk to you about my PhD project on nonlinear lattice structures. So the first thing to do really is to introduce what these structures look like. And some of them are very similar to what Krasula was talking about. We get some cylindrical lattices. And these have, as Krasula said, they can exhibit a wide range of behaviours. But the main thing that I look at is that they consist of a grid of interconnected structural elements that they are able to scissor and have a rotational degree of freedom relative to each other at their intersections. And although these structures can exhibit a wide range of behaviours, such as bistability, multi-stability, much larger elongation, and even zero stiffness, we are interested to see if we can release this constraint of these cylindrical structures and take them into a world where they're not just cylindrical, they could be spherical, they could be ellipsoidal, they could be hyperboloids, or even shapes of aerofoils, and even into wings. Can we get some of these exotic and interesting behaviours from the cylinders in these structures? So is there additional behaviour from these additional geometries? So we started modelling these structures to begin within a finite element environment, and we've came across some quite interesting problems that we didn't anticipate to begin with. And one of the main ones that we came across was the fact that the shape adaptation is so dependent not only on the geometry but also on the manufacturing process. And that manufacturing process is the difference between the zero stress state that you have. So if you've manufactured these in a straight line and then you bend them or deform them up into the shape of a lattice, whether it be a cylinder or a sphere, that induces a state of pre-stress, and that pre-stress is one of the driving factors in the deformation. So we really want to be able to ask ourselves the question, for a given geometry, whether that be a sphere, a cylinder, and a given stiffness, so that's the material structure, the cross-section, and a given pre-stress, how will this shape adapt to change? We wanted to make sure that the models that we developed were able to capture the geometry of these structures, and it was very, very easy to change them. So we developed a model that was able to predict this pre-stress in quite a nice way, looking predominantly at the geometry of these shapes, so it was easily to change. So basically we model these structures as what's known in differential geometry as a frame space curve, and these basically consist of a centre line or a line and then a frame attached to it, and that orthonormal frame moves with the structure. The frame is attached to the structure in the fact that it has one tangent vector, which is tangent to the curve, and one normal vector which points normal to the centre of the curvature. Now this frame, that's a geometric frame, is unique and it's very, very easily computed. So we like that, and we wanted to basically be able to adapt that into what we call a material frame. But the problem with this geometric frame is that it doesn't really give you any information about just the material structure. So we had to introduce a second frame, and that's what we called that the material frame. Now this frame, again, has a vector tangent to that curve, but instead of being adapted to the geometry, it's adapted to the cross-section. So that when the material or the structure bends, the rotation rates of this frame give you the standard curvatures and torsions that you would expect when you bend or twist a structure. So what we needed to be able to do is to build a model that could map from the geometric frame, which is nice and easily computed, and we could easily change the input variables, into the material frame, which gives us the behaviour of the structure. And the difference between these two frames is purely the rotation around that axis. So there's an infinite many frames, but we wanted the one that minimised the potential energy of that frame. So what we did is we formulated the model in terms of the potential energy, and we minimised that using a Rayleigh Ritz approximation subject to this rotation angle. And here you can see an example of a helix. So it's a helical centre line that goes like this, and there's a rectangular cross section. And that top line there shows you the rotation angle between the two frames, and the line below it is the derivative. And the derivative adds to the torsional term, and the angle on top is the distribution, is the rotation which distributes the curvature between the two cross sections. So this model has allowed us to, for a given C2 space curve, which allows us to define the first curve, the assembled curve or the manufactured curve, and given flexural stiffness matrix, we can find a material frame which will then produce us with the strain rates we need to model the pre-stress of this structure. This model will feed into a larger lattice model that we're working on at the moment, and it allows us to basically readily and easily change the structure and geometry without the conventional need to change all of the geometry and then remesh everything that you would do in a conventional finite element model. So thank you. If you have any questions, I'd like to hear.